My name is Thomas Edwards. I am the group leader and facility manager for the NCI's National Cryo-EM facility. And today I'm going to do a little bit of a presentation on the facility and what we do, and about our efforts working in the grid preparation space for extramural users. So. Uh, just to introduce the team. National Cryo-EM facility, sponsored by the NCI, has been in existence since May of 2017. We currently have three scientific staff, Adam, Jenny, and Tara. And then we have a program manager, Helen, and two software developers, Vladimir and Joseph. Um, so we were formed in 2017, and we are a free point of service access cryo-EM facility for extramural users, academic and nonprofit extramural users in the cancer researchers based in the United States. So when we were first started, we identified three groups of cryo-EM researchers that we were going to target and eventually serve. The first is Group 1, and those are researchers with extensive experience in cryo-EM technology. They are able to do the entire workflow from start to finish. Their issues in terms of why they would need to access us would primarily reside in inadequate access to high-end instrumentation. Then there's the Group 2 investigators, which we classified as the structural biologists, nominally in the X-ray crystallography and NMR fields. These people see value in adding cryo-EM to their toolkit. They have high expertise in protein biochemistry and purification. They would need some training in specimen preparation and data collection and some of the specific cryo-EM processing workflows. And then there's Group 3, and this is probably the most difficult group to serve. These are just biologists with important biomedical questions that want to use structural biology to solve them. They may or may not have expertise in protein purification, but they are intensely interested in adding cryo-EM methods to their toolkit, but they would need extensive training and collaboration in all aspects of the workflow, from protein purification to final interpretation of the structure. We've classified our users over the years, and primarily we have served groups 1 and 2. There are Group 3 people that are present, but in all those cases, those individuals are collaborating intensely with a expert in the cryo-EM field. Some of the Group 2 people are also collaborating with cryo-EM people, but they often also will hire a experienced postdoc in cryo-EM to start up their cryo-EM workflows in their laboratories. So currently, we've served over 60 institutions across the United States of varying levels of expertise in cryo-EM. This is our current nationwide user distribution. But we need to work hard to identify what these barriers to cryo-EM access are. And there's two primary barriers. First is that cryo-EM is incredibly expensive. High-end instruments cost in the millions of dollars. Even basic screening cryo-capable microscopes are $800 to $1 million. Then there's the annual service contracts for this equipment. For our particular Krioses that we operate, it's over $250,000 a piece. And then there's the sample preparation equipment. The standard preparative equipment for blot freezing is the VitraBot, and even that's $50,000 to $70,000, I believe. And then there's also the extensive cryo-EM training requirements, because you have to troubleshoot protein purification, be able to apply your proteins to grids with consistency, screen for suitability, operate a high-end electron microscope for your data collection, process your data to create your maps, and then build into your maps. Where the areas where the National Cryo-EM facility currently addresses, we currently, in yellow, we operate the high-end electron microscope and we provide the imaging service. That is one of the barriers we're trying to address. Um, Secondly, we are currently trying to stand up a grid preparative service for single particle workflows where people would send us samples and we would both freeze and screen the grids. And then, in addition, into the future, in terms of processing data and building maps, we hope to address these issues with educational and training workshops. Um, as providing computer infrastructure is to the entire nation is a bit onerous of a lift at this point, and we think that is best addressed by education. So, operations from the user perspective in accessing our facility, we have a website at cancer.gov/research/resources cryo-em/access. It's not a great website, not short in terms of the length of the address, but we are embedded in the NCI environment. That will have you a link to a submittable form. We have two primary requirements, well, three primary requirements really. One is that for the high-end imaging, you have to have pre-screened frozen grids of suitable quality, and the sample must be related to cancer process or treatment in some way. And this is an overly broad definition right now that we are operating with. It can involve such things as quality of life of cancer patients, such as um, nausea targets or pain targets, or even things that assist in the immune system that's not directly related to cancer patients, because cancer patients often operate with during chemotherapy with suppressed immune systems. And then the third one is no potentially infectious or toxic material. We are currently at a BSL-1 rating, so we cannot accept BSL-2 samples at this point. And so this is the extent of our application. It's a very simple and short application, and this is the entire application. We just collect some identifying information, principal investigator, institution, point of contact, NIH grant ID number. We just collect this for informational purposes. You do not need an NIH grant or any funding source to access this facility. We make no judgment on that, and there is no prioritization. It's purely for informational purposes for us. Then there's a short project description, and then you describe the physical characteristics of the sample, such as buffer conditions, size of particle, types of grids you've frozen on. And then you also have to attach low, medium, and high magnification images from your screening session. 2D classes are optional to access right now. And then attestations that it's not a BSL-2 sample. So this is pretty much the workflow from the user perspective. You know, the user will purify their sample, freeze the grids, screen the grids, and then they will judge the grids for suitability. If they are suitable grids, they will fill out that aforementioned sample information form. We will review that form and make a decision within 24 to 72 hours. Generally, if we say no, we usually ask for more supporting information or meet with the applicant to discuss what they can do to improve the application, but the vast majority of applications are approved. Once that approval is made, the user can send their grids on a dry shipper overnight and enter our active queue. So we operate with a rapid access model, entirely rapid access, first come, first serve. And you only enter that queue when we receive your grids. Additionally, a PI may only have one slot requested in our active queue at any given time. So, for instance, someone can put in 5 applications and send 5 applications worth of grids if we approve them all. But only one slot will be approved at a time. And we saw this as a compromise to allow other users to have time to access the facility so that high production labs would not monopolize our time. So, once say your first application is in the queue, once that is imaged, we'll put your next application in the queue. And the current active queue has ranged from about 2 to 8 weeks. So, and that include so within 72 hours, you can have your grids on site and in the queue. So really, it is only a 2 to 8 week wait time to access an imaging session. On the day of the imaging session, we'll load the grids. If sending multiple grids, we will do a brief screen to see which ones are and rank the best, what we feel are the best to the worst. We will then meet via a WebEx video conference to discuss the imaging session and what the user wants. And then we will start an automated imaging session, and we provide a website to monitor, but it is non-interactive. And at the end of the 48 hours, you receive a download link via Globus to get your data, and a comprehensive report will be sent a couple days later. So currently, what equipment we have 2 Titan Krios microscopes for regular imaging. Both have fringe-free alignments, and each is equipped with a Gatan K3 direct detector and bioquantum energy filter. Current general imaging collections operate at around 250 to 350 images per hour, yielding in the range from 7,000 to 12,000 for a 2-day session. We also have a Glacios microscope equipped with a Falcon 4i, multi-grid, and an Athena platform for automated screening that we are currently optimizing workflows for. A little history on the National Cryo-EM facility. We started operation May 1st, 2017. On our first microscope, we were in a leased facility in Gaithersburg, and then we renovated a site at Frederick National Lab and moved the microscope in 2019. Krios number 2 was installed in 2019, and both microscopes have 75% uptime, and that's including downtime and all downtime also includes upgrades that we have made over the years in addition to the maintenance on it. We installed a Vitrojet in September 2022 and began evaluation for a grid preparation service. We were an early adopter of the Vitrojet, so we had a lot of, so to speak, growing pains in its operation, which I'll get into later. And in March 2024, we installed a Falcon 4i camera on the Glacios, which will serve as the primary screening instrument for the grid prep program. Over the 7.5 years, we've done over 1,300 imaging sessions for 165 investigators from over 60 institutions, and we are currently averaging about 20 sessions per month, 10 per microscope. We do tilt series collection. However, it's not a requested item. We're not sure if this is due to demand itself or if people are unaware that we do offer tilt series collection, but we have done tilt series collection, and it's yielded a couple of papers. And over those years, our users have had great success. 129 publications, with 19 of those being in Cell, Nature, or Science. Over 250 structures deposited to the EM data bank, and over 4,300 citations. This is just a brief example of the many high-profile protein targets that we've done over the years, such as spike protein in the upper, COVID spike protein in the upper right, the transient receptor protein melastatin type 8, which is a cold sensing protein up in the upper left, and a variety of gene expression, histone methylation regulators as well near the bottom. And we do have some outreach. We did do a workshop a couple of years ago where we had 12 trainees out of 60 applicants. It was a 5-day workshop covering all aspects of the Cryo-EM workflow. However, we haven't made that a regular feature yet due to staffing constraints. So to talk about the grid prep back to the grid our grid prep project. So the problem. Uh, optimiz Cryo-EM is expensive. Not everyone has access to freezing equipment or screening equipment, but also there's a lot of iteration, that can occur. Often there's two types of optimizations that are going on. There's what I call the low-level problems, which is mostly the physical problems with grid preparation, and those include damage to the grid, concentration of the protein, crystalline ice formation, aggregation, those kind of things. And those can be screened for relatively quickly and relatively easily, even on a screening microscope. And then there's the high level issues, and those are more sample intrinsic to the sample itself. And those are things such as the protein can adopt an orientation bias when placed on the grid. Concentrations used can be insufficient to maintain ligand or partner binding of protein complexes, or sometimes domains of the protein complex in question are too flexible, and those can only be seen after processing at least a small data set. So for the grid preparation project, we had to decide on what equipment we would choose. Traditionally, samples are blotted using a blot plunge freezing equipment, the Vitrobot being one of the standards, but there are a variety of other ones, including manual plungers. Um, those often require a lot of samples, so 2 to 3 microliters of sample per grid. They require someone to be highly trained, highly experienced to do the fine motor manipulations to make sure that the grid doesn't, you know, get into contact with warm air or moving the grid around so it doesn't bend. And often people, even highly trained ones, will do many replicates for a given condition, such as a concentration or blot force or blot timing, um, in order to get a good grid, even among many replicates. But now, in the last 5 years, a variety of new robots that really remove the human factor have come uh, to commercial availability. Uh, and the advantages of these are consistency is dramatically improved, resulting in fewer replicates. Sample volumes are dramatically reduced. They are coupled with electronic recording so that data can be pulled into electronic notebooks. The problem with these instruments is that the price is also dramatically increased. Um, Two common robots on the market now are the Chameleon and the Vitrojet. Both have high replicability, but both do slightly different things. The Chameleon will sort of spit um, very small volumes at a descending self-wicking grid, and this grid has a bunch of nanowires on it that wick the sample away to a very thin film as it is plunging into the liquid ethane, whereas the Vitrojet will physically write the sample onto the grid with a pin and then jet ethane onto the grid prior to plunging. The Chameleon, the grids are more expensive, but the Chameleon also is meant to, with its very, very quick freezing of wicking as it is plunging into the liquid ethane, is meant to hopefully address orientation bias. Um, However, one of the disadvantages of that is that the Chameleon often requires very high sample concentration, much higher than what people are normally purifying. So we went with the Vitrojet because it does have high replicability. It has a very low sample volume requirement. 5 microliters can freeze 12 grids. Sample concentration requirements are not that different. We have seen that it needs a little bit more, up to about 2 times the concentration of what you would use on a vitrobot, but not much more than that. And we can use any grid because it freezes auto grid, so you can clip whatever grid you want, whether it's C flats, ultrafoils, hexafoils, and it has a very easy to use user interface. And that's what I'm going to talk about today. This is our Vitrojet, and the picture you can see is the pin picking up a very like picoliter sized amount of sample, which it will then physically write onto the grid. So, um, it jets liquid ethane rather, and then plunges into liquid nitrogen, and it uses an auto grid. So the in addition to the expense of the machine, in order to operate it, you also need auto grid capable loading instruments in order to screen. So. Um, and so this is a little bit of how it works in terms of how it spreads onto the grid. There is a little bit of a grid bar wicking action that does slightly thin the sample as it goes. This especially it is affected by how much the pin path overlaps. In this particular picture, we have just a straight line, but normally we do an overlapping spiral so that it takes thicker areas and kind of spreads it out a little more by going over it a little bit extra. So here we see that spreading process again. We tested extensively with beta-galactosidase. It also has an ice thickness measurement, an optical ice thickness measurement system. Although, as I'm going to show you, we don't. It is a nice guide, and I think it shows relative ice thickness nicely. I don't think it shows absolute ice thickness well as it claims. So right now, that ice thickness estimation has negative values and zero, which does measure empty holes essentially. But then it says that the ice thickness is up to 60 nanometers. We then measured this using our energy filter, and we have a very robust system of measuring ice using our energy filter that we've had in reports for our standard imaging process, and we find that it does not quite match up with the Vitrojet estimates. The Vitrojet often does, and we actually bias ourselves to trying to target thin ice that we see. The Vitrojet that in our experience is in the 50 to 75 nanometer range. And that is very consistent across the board. It's not quite ideal what we would like for single particle cryo-EM. Ideally, we would like below more towards 20 to 50 nanometers of ice thickness is where we see the best results in resolution. But even with this, we still get a decent below 3 angstrom structure of beta-galactosidase. And we've repeated this many times. This is a different sample, different day, and we still get very similar results again. And then we also get basically a 3 angstrom structure, which has been great. It's just multiple times the ice thickness estimation has not measured up. Even in this case, where we see the thickest of samples and the Vitrojet is claiming between 20 to 60, we still get more like 60 to 100. So, but we still get, even with this, we still get a very good resolution. So it's not, we are continuing to optimize, and even in the Vitrojet has settings, presets, where they say thin, medium, and thick. And when we analyzed doing the samples, we found very little difference between any of these settings. So On the one hand, we are struggling to get um, very thin ice, but on the other hand, it has been incredibly rock steady consistent. I almost don't need to do replicate grids. I can just set up, it's put in a sample, make one grid, and almost get a guaranteed decent result in terms of ac application to the grid. Right now, we are in beta testing now with real world samples. We collaborate both with the RAS group here at Frederick National Laboratory and several groups at University of Maryland. This is some of the results of a novel complex, which I sadly cannot name right now because this is very, very new data. Um, but we have the similar ice thickness, which is the middle right pane, 60 nanometers. We had very good defocus and max res, and eventually we got. I can't show the map right now, just a couple of 2D classes, but we got a 3.7 angstrom structure, which was great. And this particular structure has a compound that helps a couple of protein complexes bind together and had a local resolution of 3.5 angstroms, and we clearly see the compound. So future steps for the grid writing project, the grid preparation project is we still are constantly trying to chase getting thinner, consistent ice. We think that we've exhausted the physical parameters of the machine and are going to start pursuing sample conditions such as solvents or detergents to add. Um, we are testing all grid types. So far, results C-flats seem to produce thicker results than quantifoils, but right now with a quantifoil 200 mesh with a 2 micron hole produces the best results for us right now. And we are also continuing collaboration with a variety of FNL, and local universities to test more proteins just to see what the variability of what we're going to encounter. This helps develop our workflow to determine what the service is actually going to look like because it's not going to be an open-ended service until we solve the structure. We're going to each application is going to have a limited expectation of how many freezing sessions that we would have and how we're going to construct a deliverable data product. We also are working on establishing the automated screening pipeline with our glacios. And that's my presentation for the day.